Okay, one last chapter for the final exam, chapter 13. And in here, we will pretty much compare the parameters of low mass stars versus high mass stars. We'll discuss different scenarios, like uh, what's going to happen to a certain type of a star. And uh, I will introduce you to the process of making elements that are heavier than hydrogen and helium. Remember the Big Bang Theory? It all starts with hydrogen and helium, and then all the advanced elements, say carbon, nitrogen, oxygen, gold, silver, platinum, those are the results. It's the result of nuclear fusion that runs inside cores of stars. And without stars, essentially, we wouldn't exist because we are made of water. Water is H2O. And for oxygen, you need nuclear fusion. So we are literally made of stars that have produced all of those advanced elements, and then those stars exploded and recycled all that material back into space, and that material got in contact with uh, another hydrogen cloud. The cloud contracted, star born was born. So the cycle moves over and over again, and all of those advanced elements that you see around, if you own a piece of jewelry, or gold or silver, that's a piece of a supernova explosion that happened billions of years ago, billions of light years away. So pretty exciting chapter to go through. So let's go back to chapter 6, where we discuss the formation of a solar system and just uh, uh, start over with the birth of stars. So it is a interstellar gas cloud. You call it interstellar medium, and it all starts very cold and dense. How cold? Like we're talking, 20, 30 degrees Kelvin, and that is very close to absolute zero. Absolute zero is when you don't have any motion of molecules, which, is a very, very cold conditions, like negative 273 degrees Celsius. So uh, the star forming clouds, you can see the diagram right here. Looks like empty space, but it's kind of tricky because remember, you can't see it all. It's not visible sometimes. It's infrared part of a spectrum, so you need an infrared telescope to take a picture and see the uh, energy and matter in this area. So it is the gravity. Gravity is always the reason that forces the cloud to collapse, and the conversion of gravitational potential energy into thermal energy and kinetic energy makes it a spinning disk. It gets very hot and dense. That's where the star is born. And uh, once the condition for fusions, for nuclear fusion are met, you have the main sequence stage for a star, and that's where the conversion of hydrogen to helium begins. So gravity always wins because a little amount of photons escape those contracting clouds. Yeah, of course, it's going to take some time, but thousands of years later, you will get spinning disk, and out of few hundred solar masses to start with, you can expect more than one star to form. And even those open and global clusters with thousands of stars are also possible. It really depends on the cloud itself. So gravity has an edge over the pressure because those photons escape the cloud. I already said it. Yeah, this diagram really shows the visible versus invisible uh, part of certain area of space. So if you can't see something, it doesn't mean it's empty. There's like no such thing as empty space. You turn on the infrared and you see the missing part in the infrared part of the spectrum and see how the rest disappears because it's infrared. So don't you say empty space. It's really not empty. The concentration of matter might not be sufficient, but it's never empty. There's always, matter. There's always energy, and now dark energy that uh, you can read about the portion of the book that we can discuss because we short on time. So certain stages to go through. You have a cloud contracts, and before you enter the main sequence, you have the stage that we call protostar. So it's like a prototype of a car. If you want to introduce a new car to the general public, you make a prototype, and then you get some feedback on the prototype, and you make some corrections, and then you put it into mass production. So same thing with the protostar, which is not a star yet, but it's about to become a star. So just some more time, some more gravity to, work around, and the star eventually enters the main sequence. So let's say the cloud cannot radiate that thermal energy, those photons. What would happen to that cloud? The answer is straightforward. If gravity doesn't have an edge over internal pressure, then gravity would never win, and stars would never be born, and there would be no, solar system, us human beings, and so on. So it's good that gravity always has that little edge over internal pressure. Yeah, this is the slide from chapter 6 again. We have conservation of energy and conservation of momentum working together to see how the cloud is transformed into a disk. So for angular momentum, remember it's the mass, the rate of spin, and the way the mass is distributed. So considering all three components, you end up with a spinning flattened disk. It gets really hot in the center of the disk, and that's where the star is born. At the process of the star formation, you can also see those. Sometimes you can see jets coming out perpendicular to the disk. Those are the leftover materials coming out of newborn star. So the protostar is right there, and you can see the jets coming out. So this is pretty much how you can tell that, hey, this is a newborn star. It's about to enter the main sequence. Let's say there is no rotation to the star. Let's say that disk is not spinning. It's just a disk, and it's hot, but it's not spinning. Then what? Jets would go in multiple directions. No. Yeah, there would be no planets because we have the process of orbiting requires motion. Remember, everything that is in orbit is free falling. And if you stop moving in your trajectory, the orbiting trajectory, you just fall into that center of mass, which would be the newborn star. Let's say the Earth would stop one day, then the Earth would just fall into the sun because the sun is the center of gravity for the solar system, and we have to keep our linear velocity, tangential velocity in our orbit. We have to move very fast, so we keep on missing the sun over and over again. So with no rotation, with no spinning for that disk, all the leftover matter would just fall into a star instead of producing planetesimals, planets, and asteroids, and comets, and everything. Okay, the stage from protostar to main sequence. Yeah, everything is contracting, heating up. The conditions for fusion about 10 to 15 million degrees Kelvin. And it's very important to remember that contraction ends. There is no more contraction once the star operates on nuclear fusion. It's the fusion energy that balances uh, the energy losses as radiation from the surface. And for a sun-like star, it takes about 30 million years. By that time, all the high mass stars would already be gone from the main sequence. See how low mass stars just enter the main sequence, and high mass stars by this time are already dead. So there is gravity, shrinking gas cloud. There is uh, hot and dense core, and there is a nuclear fusion reaction. Be careful, it's fusion, not fission. Fission is for nuclear power plants, and fusion is uh, for stars. And we enter the main sequence for a long lasting time, like 95% of a star's lifespan is the main sequence stage, which is conversion of hydrogen into helium inside the core. So we're about to discuss the differences between high mass stars and low mass stars, and this diagram really shows you the the numbers. So you have just one high mass star versus hundreds of low mass stars, and only high mass stars are really capable of producing elements heavier than carbon, and everything past iron also requires an extreme mass. So it's very important that we still have those high mass stars uh, because that's the source of everything heavier uh, and more advanced than carbon. Okay, we have a little summary on the nebula, the cloud that the star is born from, and the actual process of birth. I'm pausing the lecture. Go watch the video in Canvas. Okay, we have upper limit on a star's mass and a lower limit. So for upper limit, this particular book says 150 masses of the sun. That's the upper limit. However, I've seen other papers, like research papers and books, and they say 200. So for the purpose of a test, the purpose of the final, keep in mind the number 150 masses of the sun. That's the top. That's the greatest amount. And uh, it is the degeneracy pressure that limits this particular number. And we're not going deep into quantum physics. So just upper limit is 150 masses of the sun. And the lower limit is also something that is like a universal number. It's 8% of the mass of the sun. And everything less than that, it's called a failed star. See, the stars can fail. Next time you fail a class in college, you just say, hey, stars fail. What do you want from me, right? And the failed star is called a brown dwarf, and the name speaks for itself. The color is brown. Remember, for HR diagram, we start with red, and then there's orange, and then there's yellow, right? So brown is not even a part of the HR diagram. The star can, this failed star cannot be put on an HR diagram because the color is brown and the size is very, very small. The dwarf size, it's almost there. It's almost on the main sequence, but never makes it. It's very hot. It's dense, but not hot enough to reach the fusion conditions. So everything less than this mass is not going to enter the main sequence at all. It will just stay as this hot and dense gas. You might think Jupiter, right? Jupiter is a gas giant. Jupiter is just a planet, but it would have been another star if it would reach certain conditions inside its core. So brown dwarfs are not stars. They're failed stars, and this is your lower limit for a star. Yeah, it is the degeneracy pressure slide that I used to discuss. You don't have to go deep into quantum physics. Just understand that those limits come from the idea of degeneracy pressure, and the quantum principles are good for physics class or an advanced astronomy class. So mass determines everything. Remember, mass is really the most important fundamental parameter. If a star is a low mass star, it has a certain lifestyle and lifespan. If it's a high mass star, it's a totally different scenario, even though it's the same like stars, right? They're stars and they live on nuclear fusion and everything. So the categories for stars are like technically it's three categories: low, intermediate, and high mass star. But for intermediate stars, you really don't have much of a difference between low mass stars and intermediate stars. So for test purposes, you keep in mind that there is two masses of the sun. That's for the low mass star. But in real life, think about number eight. It's the number eight that really separates eight masses of the sun that separates low mass stars versus high mass stars. Everything uh, below eight masses will just end with carbon as the highest level of fusion, maybe a little oxygen, but that's pretty much it. And everything greater than eight masses of the sun has that star has a potential to produce advanced nuclear burning and all the reactions up to iron. Okay, so we start with low mass stars, and the first two stages are the same as we discussed before. We have protostar stage and then main sequence, and the only difference between a low mass star and a high mass star would be the color. Remember the HR diagram? We have yellow, orange, and red color, and certain luminosity and surface temperature versus high mass stars, which are much hotter, much more luminous, and the size is, of course, larger, larger size, and uh, the lifespan is much less. And then it's the giant phase when the star becomes larger, like 1,000 times larger, and there's a drop in surface temperature, so it goes to a red part of the spectrum. And it is the stage when you run out of hydrogen inside its core and you go to the next level of fusion. That would be the helium to carbon. I mean, from hydrogen to helium, yeah, from helium to carbon. Um, so if a star can no longer fuse hydrogen to helium, well, you run out of hydrogen, so it's all helium. There's no opposition to gravity anymore. Gravity says thank you very much and compresses the core even further. And compression means conversion of gravitational potential energy into heat, and that heats up the core all the way to 100 million degrees. And that's where the next level of fusion begins. So the core shrinks and heats up like dramatically because, once again, gravity converts gravitational potential energy into thermal energy. And that's the mechanism to heat up the core to like a dramatic temperatures. And if the core is very hot now, then the surface and the layers next to the core also heat up, and they can heat up to 10 million degrees easily. If it's like almost 100 million in the core, it can be easily 10 million outside. And that's how the next type of fusion mm, begins. Because all you need is, 10 million, and you have 10 million outside of the core right away. This is the hydrogen in a shell fusion. So uh, there's still plenty of hydrogen around the core, and now it's a very hot environment because the core has just heated up to 100 million degrees. So you have uh, fusion outside of the core. And what's even more important, all that extra fusion that starts outside of the core just forces the outer layers to move outward, and that's how the giant is produced. The giant phase is the phase when you can't really control that extra fusion energy produced from fusion reactions, and outer layers expand. So see how interesting it is. The core contracts because there's gravity uh, squeezing it, and then it heats up, and that heat is uh, igniting the fusion outside of the core, and outer layers expand dramatically. So yeah, 100 million degrees. It's hot enough to start the helium fusion eventually in the core, and the solar thermostat was going to be, well, I say solar, it's just not solar, but any thermostat is fixed. You have gravity versus internal pressure competing once again. And of course, it takes some time to do that conversion. It doesn't start right away, but eventually we reach the next level of fusion. Um, um, for some stars, for very low mass stars, you can't even get to that level. They would be just helium white dwarfs. So it's hydrogen into helium, and that's the end of cycle for those stars. But for a sun-like star, you definitely will get to 100 million degrees Kelvin, and the sun will go into the next phase of fusion. Here is the reaction. You have 3 atoms of helium, and the output is, see, it's 3 times 4, so 1 times 12. So mass-wise, now we have the same numbers, and a little bit of mass is once again converted into energy. The E equals mc squared equation is still there. So a little bit of mass produces the energy that supports the star in its new phase of fusion. So from helium, we have the carbon element. And this is pretty much the end for a low mass star, because for the next level of fusion, you'll need 500 million degrees, which just low mass stars cannot get to. So we got helium in the core and hydrogen into helium outside of the core. So that's those are the two fusion reactions going together in a star inside a giant phase. How do you know that it's the case when the helium starts converting into carbon? We have a so-called horizontal branch. On the HR diagram, you see those stars that are drifting away from the main sequence. The main sequence would be left top to right bottom, and you see those stars drifting towards the giant phase. The horizontal branch is where you have a helium inside the core converting into carbon. So if you run out of helium for a low mass star, that's pretty much the end because gravity crushes carbon core shrinks even further, and then you got the double shell fusion star for a brief amount of time, and eventually the core collapses under the strong grip of gravity, and the star goes into what we call the planetary nebula. The process of releasing all that matter back into space, which means the death of a low mass star, and our sun will do exactly that. That carbon that was generated inside and was expelled at the moment of the death will enter, will go in contact to another interstellar gas cloud, and gravity will contract the cloud once again, and the cycle will repeat itself. So if you thinking about afterlife, you trying to figure out religion, I can tell you one thing: there is afterlife, because you and I will die, and the sun will consume the earth eventually. So a piece of your body and my body will just be expelled back into space, and then we'll get in contact with a new gas cloud. There will be another solar system 2.0, and maybe we'll be a part of a planet that will, form in that solar system. The only drawback, you have to wait for billions of years. So you can't really destroy matter. You can destroy energy. So it's just, I'm not sure about the form of life that we'll end up with, but there's definitely a conservation of matter, conservation of energy principles. So a piece of your body will be a part of solar system 2.0. That's the afterlife. I can assure you, like, it's 100% what's going to happen, because this is not the first generation of stars. It's not the last generation of stars. And sun is just one of many. Like, we are not unique. So that's what we have. Yeah, those are the diagrams for planetary nebula. The videos that I published in Canvas will show you like the dynamics of it. It's pretty cool videos. I suggest you watch all of them. And the Crash Course Astronomy is one of the best resources here. So after the explosion, all you have is a white dwarf, and that's the remnant of the star's core. It's very small, so it's dwarf. Uh, it's very hot, but it's going to gradually release all that energy into space and become black dwarf eventually. So this is a life track of a sun-like star. This is the sun that has entered the main sequence from a protostar. So then it's a horizontal branch, and then the giant, and the double shell fusion. So you have hydrogen into helium, helium into carbon, and the planetary nebula is the explosion, and then it's the white dwarf. This is the zombie. This is the remnant of the remnant phase of what used to be a star. So there's a quick summary about low mass stars for you to go check out in Canvas. So following the lecture, go watch that short video. Okay, now we move on to high mass stars, and you can see that carbon is the dead end for low mass stars, and high mass stars can produce the full spectrum of elements. So everything you see around as gold, uranium, titanium, those are the products of high mass stars. And high mass stars are pretty rare; they're not common. And they start as protostars again in the main sequence stage. Same thing, hydrogen into helium inside the core, but with a little bit of a twist. First of all, different color, and what we also call the CNO cycle. And there is a question on what is a CNO cycle, and your answer should include three things. So first of all, it's only for high mass stars. Second, it's only for main sequence. And don't just say CNO like carbon, nitrogen, and oxygen. You have to say that they are catalysts. One, two, one, two. Sorry, the headset turned off. So for CNO cycle, you don't have to remember all the reactions that are shown here. The main reaction is still hydrogen into helium because it's main sequence. So you say high mass stars, you say main sequence stage, and carbon, nitrogen, and oxygen are catalysts for the main reaction, which is hydrogen into helium. And then after that, you can see how carbon can get in contact with helium at like 500 million degrees, and boom, you got oxygen. And oxygen plus helium, 16 plus 4, that's neon, that's number 20. And neon plus helium, that's 24, that's magnesium. And that would be already billions of degrees. So all of those helium capture reactions and then advanced nuclear burning, the carbon and oxygen, 12 plus 16, that's 28, that's silicon. Oxygen and oxygen, that's sulfur. And silicon eventually give you iron. So iron is the dead end, okay? You have to keep in mind that iron is the dead end for fusion. And for the question of what's going on after iron, that's a different story. So understand that high mass stars can compress their cores to crazy conditions, and temperatures are out of this world, like billions of degrees. We started with 10 million, and now it's like 3 billion degrees, right, for the last stage. It's you got to have huge amount of mass and enormous um, luminosities, enormous temperatures. So high mass stars are capable of going through all of those reactions. That's the main difference. You start with hydrogen and helium. Oops. And then carbon is the dead end for low mass stars. And nitrogen and oxygen, neon, magnesium, and all the way to iron. Iron is the final level of fusion because iron is an energy consuming reaction. Remember, it was all energy release from the fusion. See, it was something into something plus energy, right? And this happens all the way up to iron. Once you get to iron, it's not plus energy anymore, it's minus energy. That's the big difference. And because it's minus energy, all the energy that you used to support the star in its original stable conditions, all that energy is removed, and you don't just have it anymore. So star goes nuts. Star goes through uh, uh, huge gravitational contraction. The core is squeezed like dramatically, and this is the possible supernova explosion that you can get in high mass stars. So at a certain level, like near its death, we have um, hydrogen in a shell, helium in a shell, carbon in a shell, all of those fusion reactions throughout the star. And it's the silicon fusing, producing the iron, inert iron core. This is the hottest and most dense zone. You see the size of that star would be a supergiant, of course, and hypergiants. And this is the last stage for fusion. Iron is the dead end for fusion because after that, there is no more energy release. It's the energy decrease. It's just the E equals mc squared does not work anymore at this level of fusion. And funny how iron is not the dead end just for fusion, but also for fission. You start with uranium and you split it and you split it and you split it further and further. And once you reach the iron, you also can't get any more energy out of fission reaction. So iron is the dead end for both fusion and fission. So here comes the death of a high mass star, the gravity uh, contracting the core, same as a low mass star, but the the conditions are not even close to what you see in a low mass star. The dramatic explosion is described very well in the video that we're about to watch. All the dynamics and all the processes. The idea here is that during the explosion, it's that few, like a fraction of a second through the explosion, that's the moment of time when all the elements heavier than iron are produced. Okay, it's thermonucleosynthesis, and this process is the literal, like it's the explosion process that um, gives the star the energy and power to produce elements heavier than iron. So, gold, silver, titanium, all of those precious metals were produced during the explosion of a high mass star, which has happened billions of years ago, billions of light years away. Just try to visualize that. That's just crazy. And out of a supernova explosion, you have pretty much three outcomes. The first is still a white dwarf. Then you got a neutron star, which is chapter 14, and then the black hole, which is um, chapter 15. So I encourage you to read the book all the way till the end anyways, and learn a few cool things about neutron stars and black holes. This is the diagram showing a supernova remnant. And it is, once again, the collapse of the core that uh, all the elements are produced and they are recycled back into space right away. And yeah, one guy got really lucky, an amateur astronomer, uh, got uh, got lucky just pointing his telescope into night sky and taking pictures of a supernova explosion in 1987. So you can see that this is quite a show. It's really hard to miss that. And supernova are not that common, but it's not a uh, one that's in a lifetime event. We have high mass stars blowing up from time to time. For us human beings, it's the Betelgeuse that will um, explode sooner or later, and we'll see something like that coming from the region of Betelgeuse. Don't you worry about Betelgeuse exploding. It's like 600 light years away, so we're pretty far from feeling all the effects of such an explosion. But that explosion will definitely trigger a formation of stars in that area. Uh, it will definitely rearrange energy and matter distribution in that area as well. So a lot of interesting features, but what's the most important thing is that elements heavier than iron will be produced through, in the process of that explosion, and we need them for for producing, like we need gold, silver, those precious metals to have them handy and available. Okay, time to watch a very cool video about high mass stars, the different kinds of explosions. So pausing the lecture, you go watch it in Canvas. Okay, just a few more slides. The summary, that the mass really determines everything. With high mass stars, you have much shorter lifespan, and iron is the dead end. And the supernova explosion, that's only for high mass stars. Our sun would never go through a supernova explosion. It's just not massive enough. And for low mass stars, it's much longer life, which is good because imagine the sun dying, say, I don't know, after 100 million years, there would be just no chance for us to evolve. And it's just the perfect distance away. It's perfect amount of luminosity that's not too hot, not too cold. But the sun will end as just a white dwarf, and during the process of its expansion, the Earth will become a part of the sun. So we definitely have to run away from this planet eventually and find a safer spot. So we got the stages of a low mass star and a high mass star, pretty much everything we just discussed. There is one more section in the binaries. Don't you worry about binaries on the final. I'm not including any of those questions, so consider just the first three sections. And for binaries, that's just systems of stars that can feed on each other, and you can see how uh, there is another option for fusion because companion star just steals matter and uh, converts that into energy. So no questions from section 4 on the final. So don't worry about it. So this concludes the class. Congratulations, we survived. I still suggest you read about neutron stars, black holes, and cosmology. Like four more chapters. Very good read. And of course, you can take a physics class that I teach at different colleges. Uh, I suggest you don't stop research, doing science. It's very rewarding. You learn a lot of cool facts about the nature. Um, so yeah, leave a comment on ratemyprofessor.com if you find this interesting. And it was a pleasure to be your instructor. Wishing you all the best. If you score the overall A in my classes, you can ask for a recommendation letter. So yeah, um, best of luck. See you next time in my classes. Take care.